All right, welcome back. We are looking at section 7.2 in exponential algebra, a review of scientific notation. I want you to take just a couple minutes here, pause the video, and try the two review questions. And when you have your answers, go ahead and turn the video back on. All right, hopefully you noticed in the first one that all of this is being raised to the 0 power. You have a negative 23, x, y, and z. It doesn't even matter what those are. That whole quantity is being raised to the 0 power. And yesterday we learned that anything to the 0 power is a 1. The negative out front needs to be brought down, so we end up with a -1 answer. In our second review question, we do have another example of that 0 exponent rule. P to the 0 power would just be a 1, and multiplying by 1 doesn't change our answer at all. So looking at the other pieces, you'll notice a few negative exponents. Now do be careful because there's a -2 right here, but that negative is not part of the exponent, so it is not going to move its position at all. The only pieces in this case that should have moved are the n's and the q's. So let's start by rewriting that. We're going to have a 2 on top in the numerator. We still have the m squared in the numerator. The n to the third is going to move to the bottom denominator. And then we already said p to the 0 is just a 1. In the denominator, we had an 8. We had a q to the -5, so that is going to have to shift up to the numerator. And now it's raised to a +5 power. And then we do have that -2 that's being squared in the denominator as well. All right, so simplifying. There's really nothing we can do on top in this next step. So 2m squared q to the 5th will still be there. But we can simplify some of the denominator. The -2 squared is 4. So we have n cubed times 8 times 4. And 8 times 4 is 32. So now we have 2m squared q to the 5th divided by 32n cubed. And the only thing that we can reduce now is the 2 and the 32. We can divide both of those by a 2, which makes that 1 and that 16. So our final answer is m squared q to the 5th divided by 16n cubed. All right, if you were having trouble with either of those, make sure you check in with me and we can see what we can do to help you out. All right, we said our topic today was scientific notation. Our objectives here is to be able to write numbers in scientific notation and also to be able to convert them back into standard form and from standard form into scientific and back and forth. The last objective today is to perform operations on numbers that are in scientific notation. So, for example, how do we multiply two numbers that are in scientific notation? All right. Now, why do we even need to know scientific notation? Because often we're dealing with very large or very small numbers. So, scientific notation is a way to make these more workable. Our little intro question. Determine how many times your heart beats in 100 years if it averages 80 beats per minute. So if you think about that, we have to somehow get from 80 beats per minute to how many beats we have in 100 years. We have to do some converting. So let's start out. We've got 80 beats per minute. Now, how many minutes are there in an hour? All right. If we have 60 minutes in an hour, what's going to happen when we multiply that is this minutes term will drop out. So 80 times 60, that will give us how many beats we have per hour. Okay? But we still have to get to years. So our next conversion, we have hours. Well, we know that there are 24 hours per day. So now we've converted it into beats per day. We know that we have 365 days per year. So we've converted now into beats per year. And we want to do this for 100 years. So the question is, how many times will your heart beat in 100 years? Notice that beats is the only unit term that we have left. So grab a calculator. we are going to multiply. We've got an 80, a 60, 24, 365, and 100. All right, your calculator, if it can handle this large number, should look like this. We've got 4,204,800,000 beats in that time frame, in that 100 years. That's a really huge number. So this is a reason that we have scientific notation, because we don't want to work with numbers that are that huge. All right, so scientific notation. A number written as a product of two numbers. Number product means that we are multiplying. I'll say two terms. And our form a times 10 to a power. All right, that is the basic form for scientific notation. Now there are a couple restrictions. Our a value has to be greater than or equal to 1, but still under 10. In other words, you can go anywhere from 1 to 9.999999999. You just can't move to 10, which means that this first, what we call the leading term here, this a, can only have one decimal place. The other restriction is that our power, that n, must be an integer. And remember, integers are things like -3, 2, -1, 0, 1, 2, 3, etc. All right, so first example here we're going to look at is these are not in scientific notation. What is wrong with them? Why are they not in that right form? All right, our first one, we have 0.98 times 10 to the 8th. It kind of looks like it's in scientific notation, but notice this right here. Our a value has to start with 1 and go up to that 9.99999. So we cannot have 0.98. It's too small. And it doesn't technically have to be bigger. It could actually equal 1. So let's say that not a is greater than or equal to 1. Our second example. The first part is fine. 1.4, that fits. It's a number between 1 and 10. The problem is right here. 1/2 is not an integer. All right, so we cannot have that as the type of exponent for 10. And then the third example, we have 4.5 to the 10th power. It has a 10 in it. It has the 4.5, a number between 1 and 10. But in our scientific notation, we have to have it being multiplied by 10 to a power. So it is not the product of a number and 10 to a power. Okay? All right, now, how do we go back and forth between scientific and standard notation? The first ones here are all in standard notation, decimal form. We want to put them in scientific form. All right, we have some large numbers and we have some very tiny numbers. The first one's fairly large, 678,000. Scientific notation says that our decimal has to be right there. We have to have it as 6.78. You do not need the extra zeros at the end. We just need to include all of the digits here. Only one space before our decimal point. It needs to be a number between 1 and 10. All right, so then the next part of this is we have to figure out, well, how many spaces did we move that decimal? Let me erase this here so we can see it a little better. We started out with the decimal point right there at the end. And if you count, we move to the left 1, 2, 3, 4, 5 spaces to have it land between the 6 and the 7. So we're going to need a 5 up here as our exponent, because multiplying 6.78 times 10 times 10 times 10 times 10 times 10, 5 of those 10s, will move that decimal back out to where it started. Okay? Question B, notice, is a very tiny number. So our decimal has to move. Again, we can only have one digit, one non-zero digit before the decimal point. So we need our decimal point to be between the 3 and the 2. So we're going to have 3.2 times 10 to some power. Now, with a tiny number, we are actually having to move that decimal to the right to rewrite it in scientific notation. 1, 2, 3, 4, 5 spaces to the right. But if I leave it like that, when I rewrite this, 3.2 times 10 to the 5th, the decimal would move further to the right. I need to indicate that that decimal has to move back to the left to get back to my original number. So that's where a negative exponent will come in. It means we're really dividing by 10 to the 5th. All right, following that negative rule from yesterday. So very large numbers will have positive exponents. And small numbers will have negative. All right, so we have 2 more examples. Go ahead and pause the video and try them, and then come back and we'll check. All right, we have a large number here. So when we convert this, we are going to have times 10 to a positive exponent. We need to figure out how many spaces we move to get that decimal in the right spot. It needs to land between the 5 and the 1. All right, now in this case, there is a 1 and a 4 after that decimal. We want to include all of the digits until we get to just the plain zeros. Then we don't need to include those. So we have 5.14 times 10 to a positive power. That positive power is how many spaces we had to move. All right, so counting. We moved 3 to get around those zeros. We moved 3 more to get around those. So we've moved a total of 6, and then 1 more. So we need a 7 as our exponent. And in our last example in this question, we have a 7, but it's with lots of zeros in front. Now you can write 7 or 7.0 if you want. All right, I would accept either one. In this case, though, we are going to have a negative exponent because it's a very tiny number. How many spaces do we move? 1, 2, 3, 4, 5, 6, 7. So we're going to have negative 7 as our exponent. All right, our next example, we are going in the reverse direction. Now we are giving you the question written in scientific notation, and we want you to figure out what is that in standard form. So 5.5 times 10 to the 6th. Since we have a positive exponent, it's going to be a large number. That means our decimal has to move to the right. All right, so we're going to start out with that 5.5. Notice I didn't put the decimal in because I'm going to move it 6 places to the right. So it was here between the 5s. We're going to move it 1, 2, 3, 4, 5, 6 spots. And all of those little loops would have a 0 in there. All right, now if you're counting the zeros, you should see 5 zeros. Common mistake is that students say it has a power of 6, so we need 6 zeros. It's not how many zeros you add, it's how many spaces you move. And we needed to move 1 space to get beyond that second 5. So we really only need 5 more zeros. So we have 5, 5, 0, 0, 0, 0, 0. Putting our commas in after each 3, starting from the right-hand side, would look like that. All right, the second example. We're looking at the weight of an ant. It's very tiny, 3.1 times 10 to the negative 3. Okay, so small number means that we have a negative exponent, right? So if you see a negative exponent, our answer should end up being a small number. We have 3.1 times 10 to the negative 3. We need to move the decimal 3 units to the left. So again, that doesn't mean we need 3 zeros. It means we need to move 3 spaces. All right, so we have a 3 and we have a 1. Our first space is just to get beyond that 3. We then need 2 more spaces before we get to our decimal point. So we only need 2 zeros to get our final answer. So 0.0031. All right, challenge question. Write 45 times 10 to the 5th in proper scientific notation. Well, first of all, you have to figure out what's wrong with it. Why is it not in proper notation right now? And the answer is right there. 45 is too big. It needs to be a number between 1 and 10. So we really want this to be 4.5. Now let's think about what this number is in regular notation, in standard form. 45 times 10 to the 5th means you have 45, and then we have to move from here 5 spaces to the right. So from here, we have to go 1, 2, 3, 4, 5. Okay? Now, if we wanted to put it in proper notation, scientific notation, we want our decimal to be right there. So we're going to write this as 4.5, and then how many spaces did we have to move? 1, 2, 3, 4, 5, 6 to get that decimal to land in the right spot. So that would be the correct scientific notation for that. All right, our next task is to compare numbers that are written in scientific notation. In this example, it says the map shows 4 major world oceans and their surface areas. We want to order them from least to greatest. Now the key here is to focus first on your powers of 10. Okay, so in our first example, we have a 7 here as our power. We have a 7 here. And these two, it's a little blurry, but these two are both 8s for exponents. So when you look at the numbers, they all are a single digit. 1 in front there, 7 there, 1 there, 1 there. There's just 1 digit before, so we can start with our powers of 10. The 10 to the 7ths are going to be smaller than the 10 to the 8ths. So we know that these two up here are going to have to come first. And then we can move to the number, the first part of that number. All right, so our first number, we have a 1.41 and we have a 7.49. So obviously the 1.41 is smaller than 7.49. So Arctic Ocean would be smallest. At 1.41 times 10 to the 7th. And then the Indian Ocean would be next at 7.49 times 10 to the 7th. All right, then looking at our second two, the Atlantic and the Pacific, both have a 10 to the 8th. So we can compare the front numbers. Is 1.06 smaller or larger than 1.8? Well, if you think of money, in the first case you have $1.06. In the second case you have $1.80. And $1.80 is bigger. So we're going from smallest to largest. Atlantic would be next at 1.06 times 10 to the 8th. And then Pacific is our final one, the largest. All right. It says multiply and write your answer in scientific notation. Now the common mistake is for students to see that front number, in this first one a 3, and think that they have to distribute. But you only distribute if this is a positive or negative in here. It does not work for multiplication. So if we think of this in a different format, we are really saying we're taking 3 times 5.4 times 10 to the 6th. All right, and we can simply multiply these two parts together. So grab your calculators if you need to, otherwise just multiply by hand. 5.4 times 3. 3 times 4 is 12, carry our 1. 3 times 5 is 15, plus the 1 is 16. We had one decimal spot, so we have one space after our decimal. We end up with 16.2 times 10 to the 6th. But is that in proper scientific notation? No, because this is too big. What we really want is for our decimal point to be right there. So we need to convert this 1.62, and now our trick is we have to figure out what's our new power of 10. If you think about what the 6 originally would have meant, we would be moving 6 places this way. If we move back 1 to get out to this same spot, we now have to move 7 spaces. So we need a power of 7. All right. Our last example. Only thing different in this one is we have a negative exponent here. So we have 2 times 9.8 times 10 to the negative 5. All right. 2 times 9.8 is 19.6. All right. And again, we need to change that decimal location. We need it to be there. So 1.96 times 10 to some power. All right, what will that power be? Well, originally we were going 5 places since it's negative to the left. So 1, 2, 3, 4, 5. If we move our decimal to where the red X is, then we only have 1, 2, 3, 4 spaces to move to get to where we're supposed to be. So we only need a negative 4 as our exponent. All right, in your notes, there should be a summary page or a summary section. Our objectives again were to write numbers in scientific notation and to convert them back and forth between that and standard form. And then also to look at how do we multiply numbers like we just did here that are in scientific notation. So take a minute and fill in your summary, and then go ahead and rate yourself on that scale of 0 to 4. Remember, a 0 meaning that even with assistance, I can't complete the process. A 1, I can start them, but I can't continue. I don't know how to finish them. A 2 means I can finish the question with a little bit of assistance. A 3, I can do it on my own. And a 4, I know it so well I could teach someone else. All right, your assignment. Will be worksheet 7.2. Make sure that you are completing your summary while I pass those out.